Korea Hydro and Nuclear Power's innovative SMR is a small modular reactor that not only reduced the size of the reactor, but also increased its safety by integrating major devices into one integrated type. Innovative SMR is protected by large structures called containment vessel. The containment vessel is 34.9 meters high, 9 meters upper exterior diameter, and 5 meters lower exterior diameter, and is designed to withstand a design pressure of 5 megapascal and a design temperature of 350 degrees Celsius. It also consists of a cylindrical steel shell and a hemisphere upper-lower head, which maintains structural soundness in the event of an accident, prevents uncontrolled radioactive materials from being released into the environment, and can withstand internal pressure and temperature rise due to loss of coolant accident. Inside the containment vessel, there is a reactor vessel, including one in which a nuclear reaction actually occurs. The reactor vessel is manufactured with a height of 30-meter upper outer diameter of 5.5 meters, a lower outer diameter of 4 meters, and a maximum outer diameter of 7.6 meters, and is designed to withstand a design pressure of 17 megapascal. This is constructed in a shape with a hemispherical lower head welded to a vertical cylindrical vessel and forms a primary boundary with the reactor vessel head. The reactor vessel is responsible for enduring a lot of thermal energy generated by nuclear reactions and shielding radiation and radioactive materials from leaving the reactor. The pressurizer, located at the top of the reactor vessel, is one of the main components of the reactor coolant system. That functions to pressurize the reactor coolant system under high pressure, allowing the coolant to remain supercooled under high temperature conditions. And the pressurizer has a volume of 64.36 cubic meters to accommodate the volume change of the reactor coolant. Around the pressurizer, 4 reactor coolant pumps are installed. The reactor coolant pumps are installed vertically on the upper structure of the reactor opening and closing head, and these pumps are designed with a rated flow rate capable of sending 5,580 cubic meters per hour in the form of a canned motor pump, a design pressure of 17 megapascal, and a design temperature of 360 degrees Celsius. Pump has a rotational speed of 1,780 RPM and is measured by a sensor installed at the top of the motor. The reactor coolant pump circulates the reactor coolant to the top of the steam generator to heat exchange with the secondary coolant on the steam generator tube side, which is cooled and reheated as it passes through the steam generator. The lower part of the reactor opening and closing head contains a power cable of the control element drive mechanism and a cable assembly that serves as the route for the positioning cable. The penetration nozzle of the cable assembly is designed to have an outer diameter of 190 millimeters, taking into account the size of the penetration of the reactor closure head. This allows for the installation of 4 cables per penetrating nozzle. A total of 28 through nozzles are installed in the cable assembly, acting as a path for cables required by 49 control element drive mechanisms. An in-vessel control element drive mechanism is installed under the cable assembly that is designed with a design temperature of 360 degrees Celsius, a design pressure of 17 megapascal, and a stroke of 2.4 meters, with a drive speed that can move up to 500 millimeters per minute. The CEDM operates by activating parts made of magnetic materials and applying a local magnetic field. It plays a role in controlling the linear motion of the control element assembly by the operation signal received from the control system of the CEDM. The steam generator surrounds the CEDM inside the reactor vessel that is designed in a spiral perfusion type with a design pressure of 17 megapascal and a design temperature of 360 degrees Celsius, and consists of 5,128 heat transfer tubes with an average length of 21.2 meters. The steam generator is installed in the annular space between the core support body and the reactor vessel and consists of 8 water supply headers, 8 steam headers, a steam generator tube, and tube supports. During normal operation that receives high temperature and high pressure coolant heated in the core to turn the water supply into superheated steam, and even removes residual heat from the primary system during shutdown or transient state of the reactor. At the bottom of the reactor vessel, a nuclear fuel assembly produces energy through nuclear reactions in the core. The nuclear fuel assembly is designed with 17 × 17 nuclear dioxide nuclear fuel rods guaranteed by commercial pressurized light water reactors, and each nuclear fuel assembly consists of 260 nuclear fuel rods with an effective height of 2.4 meters, 28 guide tubes, and a rectangular array of instrumentation tubes. Nuclear fuel assembly is designed to accommodate output changes in a flexible load operation range of 20 to 100%.